Namaskar and welcome back to the course in statistical mechanics of phases and phase transitions. We are discussing the renormalization group as applied to the Owen-Ginsburg-Landau theory and formulated by Wilson. And we explored what happens at what is called as the tree level. So what happens in this context is the modes of your system are broken up into long wavelength modes and the short wavelength modes. And we simply ignore the effect of the short wavelength modes on the long wavelength modes, and this is what we call as tree level renormalization. And this gives us the exponents associated with different operators are simply the exponents that are related to the dimensional considerations, and therefore they will just turn out to be the momentum dimension of the corresponding operator. So around the Gaussian fixed point, we found that apart from the T phi square term, we found that there are no relevant operators if we are in dimensions greater than or equal to 4. There is only one relevant operator when we are in dimension 3, and since the Gaussian fixed point has two relevant operators in d equal to 3, we know that there should be some other fixed point close by, or we hope that we can find a fixed point close by which has only one relevant operator, which could then describe the critical point of the Owen theory in say d equal to 3. So how we motivated this was to look at the tree level renormalization group flow in d equal to 3, and so you see that if you start from this Gaussian fixed point, you are flowing away, and the idea is that if we follow one of these lines, we will end up at some fixed point. So imagine that this is some kind of fluid flow and there is a source here and this fluid is flowing out, and the idea is that we want to go to some point where there is a sink, that is this will flow and stop somewhere, at least in one direction. In the other direction it may flow away, it will be a source in the other direction, right? And so this is what we are after, and for this we need to do calculations at finite u, that is this the so called phi 4 term. So that's in a manner of speaking the modes are interacting with each other, and this is what we developed some technique for in the last lecture. So what we did was we figured out a way to do perturbative calculations in u, and we realized that we can organize the calculations using Feynman diagrams. So that's the diagrammatic method. And in computing the diagrams, we found that there are connected diagrams and disconnected diagrams, and the importance of connected diagrams was highlighted in the last lecture, and we pointed out the linked cluster theorem. So this is where we are, and we are sort of hunting for a new fixed point, and no surprise here, in this lecture we will actually find that fixed point, and in fact we will actually compute the critical properties of the Owen-Ginsburg-Landau theory in this lecture. So in many ways this is a very exciting lecture in the sense that we are going to see the fruits of all the work we have put in all these lectures previous. A lot of techniques and concepts are developed, and this will culminate in the results that we will be showing today. Okay. So let us quickly set the stage here. So we have this Owen vector field phi of x, and we have an action associated with that, which is the Ginsburg-Landau theory. So there is the the quadratic piece, so that this is what we call as S0 phi, and then there is this quartic piece which we call SU, and there is a cutoff lambda. As usual, cutoff is the central point here, that these theories are defined with a cutoff, and the dimensionless coupling constant associated with these coupling constants are T and U, and so this theory can be described by a point in this in the space of theories as 1 is this coefficient, T is this, and U is the coefficient of phi to the 4, and like we said, we don't really need to add any more terms to this. Because at tree level they are irrelevant, and there are no other relevant operators other than these. So this is the idea. So our goal of course is to figure out what is this renormalization group transformation. So if I do the scale transformation with the scale factor S, this point P in this theory space will move to some other point P of S, and we would like to find what that point is, or equivalently we want to find what is called as the beta function. And if we solve for the fixed points of the beta functions, namely beta p star equal to 0, we can find the fixed points of the renormalization group flow, and that will allow us to say something about the critical properties if we find some interesting new fixed points. So the strategy, as we just briefly mentioned, is that we take the field phi of x and we break it up into what we call as long wavelength pieces, or the slow modes as they are called, and the fast modes, or the short wavelength highly fluctuating pieces. So this phi less than has all the fields with momenta greater than momenta less than lambda by s, and this phi greater than, which has these high momenta, namely something between lambda by s and lambda, which is close to the cutoff. They are the ones that are the highly fluctuating ones. And what we are really interested in finding out is, what is the effect of these long wavelength modes on the the short wavelength fluctuations on the long wavelength modes? How do they change the physics of those modes? In the sense that the RG transformation actually precisely figures out, when you do scaling, what do the short wavelength modes do to your long wavelength modes. In fact, we will find out that all this anomalous physics that we find in critical points, etc., they can all be traced to this. Okay, all right. So how do we do this analysis? So what we do is, we say we will write this action as phi less than plus phi greater than, and by the very definition of this is S naught of phi less than plus phi greater than, and SU of phi less than plus phi greater than. And then what we will do is, we will figure out a piece that depends only on phi less than, and in fact it will have exactly the same form as this theory, except that there will be phi less than here, and whatever extra piece we get, we will lump it into this u tilde phi less than phi greater than. Okay, so that is what we will do. Okay, let us continue. We have to obtain this u tilde explicitly, because we have to actually do the calculations term by term in u tilde. And what we do is, we first note that S naught phi less than phi greater than simply splits, so it becomes S naught of phi less than plus S naught of phi greater than, and this is simply the fact that plane waves with different wavelengths are orthogonal to each other. I mean, it's just following from that. Okay, so you can check this. This is what happens. There's these fields don't have any common momenta, if you wish. So the plane wave content of each of these fields is very different, and therefore they are orthogonal to each other. Okay. If you look at the SU term, you need some patience, and you may need some sheets of paper if you want to work it out. So you see, if you expand this out, you will see that this is a square of a square. So if you expand it out fully, you will get 6 terms. So one of those terms is just phi less than to the power 4, and you see that by itself will simply go in with the SU less than, because you see that is exactly SU with phi less than as the argument, and the remainder 5 terms that are here, namely all the things that I have listed in this line, they are clubbed in as this term, right. So this is what we call as U phi less than phi greater than. Okay, so this is SU phi less than, and there is S0 phi less than, S0 phi greater than, and U phi less than phi greater than. So we can arrange this whole thing very nicely in this fashion. So this was our original definition, S phi less than plus U tilde phi less than phi greater than, and now this is simply S phi less than. How do I get S phi less than? That is because it is S0 phi less than plus this SU phi less than. So that is what is here, and what is remaining is S0 phi greater than and U phi less than phi greater than. So this entire thing is U tilde phi less than phi greater than. Okay, just some little bookkeeping, we need this for doing our calculations. Okay, now what we are going to do is, we are going to try to find the effective action of the phi less than modes when we integrate out the phi greater than modes. Okay, so how do we do this? To obtain the effective action, we just go through our standard procedure. So we take this path integral and integrate both over the phi less than and phi greater than. functional integral is integrated with these two things. And I just stick in that formula that I had for s phi less than plus phi greater than, which we have now written in this form, that is s phi less than plus u tilde phi less than phi greater than. Now we rewrite this, so this s phi less than does not depend on this functional piece here, so you pull it out, and then this is functional integral over phi greater than modes. Now I am writing explicitly what is u tilde, and this is e to the minus s0 phi greater than u phi less than phi greater than, right. And now remarkably we see that this s0 phi greater than is a Gaussian theory, with Gaussian meaning quadratic theory, with only high wavelength modes, namely modes with between lambda by s and lambda. So because it is a quadratic theory, it has all nice properties of a nice Gaussian theory, and we can, any expectation value of any number of operators can be calculated using Wick's theorem and so on. And therefore we observe that if I can write a partition function associated with this Gaussian theory as z0 greater than, that is the partition function associated with just this theory, then this functional integral can be thought of as a expectation value on the ensemble obtained by S0 phi greater than. So in the last lecture we did it over the full Gaussian theory. So now we are doing it only on the Gaussian theory associated with the highly fluctuating short wavelength modes. That's the only difference, but other than that conceptually it's exactly the same thing. So this is what we get for this term. Okay. So in the last step, like I said, we noticed that S0 phi greater than is a quadratic theory, and the expectation value on this is the expectation value on the ensemble generated by S0 phi greater than, and integration is done over just the phi greater than modes. Okay, if you have understood this, then it's very easy to see that this expectation value of 0 greater than, which means we are integrating over the greater than modes, can be done by expanding this in a power series, and every time you see terms associated with phi greater than, we can use Wick's theorem associated with phi greater than, and with the S0 phi greater than ensemble is what I mean, and we can evaluate these terms, and you will see that the answer will depend only on phi less than modes. So phi less than mode in some sense are some sort of external fields that are acting on the phi greater than fields, if you wish, and so the answer will depend on phi less than, and it will be some functional of the phi less than fields, and that functional we are calling script A of phi less than. Okay. So this is a formal statement. It's not always easy to do this, but at least I will show in this lecture that we can do this up to some order in U we can do. Okay. All right. So now it's very easy to see that once we have done this calculation, you will see that this can be written as A here, and I just exponentiate that with a negative sign. So I will get an effective action of phi less than is this S phi less than minus log A phi less than, right. So this thing is A phi less than, so I write it as e to the minus of minus log A phi less than, and therefore that is the effective action. Now you might wonder what happened to this. So strictly I should exponentiate that as well and shift this action by some constant term. See, this isn't a constant because it does not depend on the phi less than fields, but we have been just dropping constants in this normalization group idea, because you know those constants will simply add to some analytical part of the free energy. So we will just continue to do that because we know that it's not going to harm us in any way. So we will just drop that constant term, which is the negative log of this Z0. Okay, so that is the formal answer. So you may think, okay, we are done. Not quite, because we don't know the exact form of this A phi less than. We have just written down some symbol to denote that it can be done. We haven't done it yet. So the question is, how do we get some expression for this term? Okay, so here what we are going to do is we are going to again use all the techniques that we developed in the end of last lecture. So we notice that A phi less than can be expanded as expectation value of U phi less than phi greater than, evaluated on the greater than ensemble, the 0 or greater than ensemble, and I am simply writing out the expansion plus dot 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 strictly I should say, but this is only up to order U square, right. Now minus log of this is something that we know how to do. This is the trick that we have learned before. When I take log of this, what happens? We know that each of these p's will have both connected and disconnected diagrams. So when you expand this out, you will get this term by itself, and minus of this minus that, which is the square of the first order term, and so all the disconnected pieces that arise from here will get cancelled out by the square of this term, and this sort of happens telescopically if you wish. Higher order terms will cancel the higher power expectation values, disconnected terms, etc. And finally, if you stop at order U square, you can just rewrite this as this expectation value 0, but keeping only the connected diagrams. Okay, so we are going to use the link cluster theorem. We are going to put the link cluster theorem to good use in this discussion. So that is the result. Okay, so if I now work out what happens to the effective action for the phi less than fields, I have got my expression for log A at least up to order U square, little u square, or dimensionless coupling constant, and you see that it is this. So now what we are going to do is we are going to take term by term and we are going to start evaluating it, and we are going to see what physics we can learn from this. Okay. So now I have to show you a bunch of technical things that we need. I will not spend a lot of time on this, but you should try to make sure that you at least get both the notation as well as the gist of the formulae, and you should definitely try to work these things out yourself at your own time. Okay. So what I would like to do is I would like to find the expectation value of this. So okay, there is a small thing that we have to add here. So this is on 0 greater than ensemble, that is this expectation value is taken on the 0 greater than ensemble. That by definition is this delta alpha alpha prime, because the different modes do not talk to each other even for this greater than ensemble. This is g greater than x1 x2. Now what is this g greater than x1 x2? It is the Green's function of the short wavelength modes. So if you simply go and do Fourier analysis and work it out yourself, what you will find is that this integral now will occur only in the momentum shell between lambda by s and lambda. So all the k's are within that, and it is simply the Fourier transform of 1 by k square plus t lambda square, the free theory, right. So it is the propagator of the free theory, and then I just integrate this out. Okay. Now if you integrate this out, you will get some form for this, and it is not that we will always need the full form of this, but we will need certain quantities associated with that. In particular, we will need g greater than when both x's are evaluated at the same place. That means that you just put x equal to x here, so you will get 0, and that will turn out to be this quantity. And if you realize that this does not depend on the angle at all, the argument in the k space, so you can just do the angular integral, and that will turn out to be the surface area of the d minus 1 dimensional sphere, that is SD, and this 2 pi to the d, which is coming from our usual Fourier transform definition. So this quantity we have already introduced these things in previous lectures, so I am not explicitly showing you these things. But SD by 2 pi to the d is, I will just call it CD for now. Okay, these are some dimension dependent constants. So if you evaluate this, you will see that this is CD lambda to the d minus 1. So you see when I do this integral, I have d powers of k in the numerator and 2 powers of k in the denominator. I can use lambda to make this dimensionless, and therefore I will get lambda to the d minus 2 as we see here. And what we will end up seeing is that this integral is actually a very standard nice looking integral, which is 1 by s to 1 dy y to the d minus 1, everything is dimensionless, t little t is the coupling constant which is dimensionless, y square plus t to the power a. Now for this integral, if I want to compute g 0 0, is evaluated with a equal to 1, and that is what we see here. Okay, so this is very useful, and you will see it's also an important thing to kind of remember, because this formula will show up when we do the calculations. Okay, very good. So the second nice result we need is that the integral over r. So suppose I suppose I keep x2 equal to 0 and I run x1 and do the integral of g of greater than r, that will turn out to be 0, and you can ask yourself why that's the case. It's yeah, you can think about that. Okay, and another very interesting thing is I need sort of the square of this integrated over r, and that will turn out to be cd lambda to the d minus 4 idst2. So it's exactly the same I function with power 2 here instead of power 1. Okay, so that's the results. So these are the results that we need, and we will use them when we are going to do the R calculations. Okay, so these are the results that we will need for our calculations. Okay, so what we'll start by doing is we'll start computing the first order term, namely order u term, and what I'm going to do is I'm going to just show you an example of how you do this by just writing out the full expression here. So if you look at there are these 5 terms, 1, 2, 3, 4, 5. Each of these 5 terms can be represented by diagrams. How do you look at this term? So this is phi less than dot phi greater than. So what happens is I have 2 legs on this. So this is a phi less than leg, and that is a phi greater than leg, and alpha means that there is a dot product between them. So that's contracted in the ON indices. So you have this blue line with the red line here, and this blue line, red line is the square term has the other term associated with that, so that is that. So this term is represented by this diagram. The second term here is phi greater than to the power 4, and that is represented by all 4 red, because all the fields phi that enter into this vertex are the fast fields or the short wavelength fields. If I look at this term, there is a phi less than square, phi less than dot phi greater than, so you will see that is represented in this way. And if you look at this term, it is phi less than square, phi greater than square, so alpha is on the blue lines and gamma is on the red lines, and so on. So you get these terms. Okay. So now what we're going to do is we're going to start with this term, and we are going to contract, we are going to use Wick's theorem to contract this. So what happens? I have to contract, so I am taking this particular term and I have to contract this line here. So when I do that, I will get delta alpha gamma, and the contraction of this is in the 0 greater than ensemble. So I will end up getting this Green's function, which is evaluated at the same positions that I have. And this is the phi alpha phi gamma, delta alpha gamma. When you contract with this, it will just become phi less than square evaluated at x. And this whole integral is something that this whole term that we have seen this term before. That's what we showed in the previous slide, and we can extract that, and that will turn out to be this value out here. Okay. So this is the result that we will get for this calculation. Okay. So remember, there are 5 terms, so we have to do term by term. So it's a bit of work. So the second term is we have to compute the Wick's theorem of phi greater than to the power 4. Now you may be very enthusiastic because you may want to do these kind of calculations, but it's totally unnecessary to do this here, because this term will produce no term that has any phi greater than term in it. So in other words, it will contribute to the constant piece added to the free energy of the system, and an analytical piece nonetheless. So we don't care about it. So we just not even bother cancelling this. We just drop the term. Okay. Now what about this term? So this term is 4 phi greater than, phi less than, and phi greater than. Right. So there are 3 powers of phi less than and 1 power of phi greater than. Right. Now we know that if I suppose I were to integrate out the phi greater than, I will get some answer, let us say. So this will be now a term which is 3 powers of phi, but we know that that cannot implement, okay, at least the way it is written out here will not be able to implement any ON symmetry. So this will be simply drop out because the system has some ON symmetry. Now when you look at the fourth term, you see that this will have phi less than square, phi greater than square. So now I have to take this term number 4 here and I have to contract these, and when I contract these, something interesting will happen. This contraction will produce delta gamma gamma, which will produce a factor of n, where n is related to the symmetry. So the number of components of ON, right. So you will suddenly see that the symmetry will rear its head for the first time in a sense, right. So you will see this happening. And such a diagram is called a tadpole diagram. So as you can see, the physicists, they work very hard, and you see when they see things like this, they get excited and they give interesting names. Alright. And finally, when you look at this the fifth term here, you will see that that again has 3 powers of phi greater than, and so it will integrate to 0, it will not produce any non-trivial term, and so you will end up getting something that vanishes. So if I stop at this order u, I will see that I have changed my effective action. So let us see what has not changed. So the gradient phi less than square has not changed. The u phi to the 4 term has not changed because we have not generated any new additional interactions or phi 4 kind of terms here. But we have generated these new terms which change the value of t. So now you see this spectacularly interesting phenomenon, which is the following, that when you do this process of coarse graining or integrating out, the short wavelength modes in your system change the parameters associated with the longer wavelength modes. They change the effective interactions or coupling constants of the longer wavelength modes. Right, and this is the crux of the physics here, right. So you will see that this t, the new t that you get for the shorter wavelength, the longer wavelength phi less than, those will be determined by not only the old t but also the u that you had in the problem, the phi 4 term. Okay. So naively you might think, how is it possible that physics wise you cannot add t physical and u physical because they have different dimensions. But what happens here is these diagrams will exactly produce the required powers of lambda. This is the power of this game. So you start off with lambda to the power 4 minus d, but these diagrams actually produced enough powers of lambda to actually give you the correct power of lambda square that is multiplying the phi less than square term. So this is the power of this method, that it is able to capture what is the effect of the short wavelength modes on the longer wavelength modes. And if you stop at order u, this is the effective action of the longer wavelength degrees of freedom. And you see I have a theory for the longer wavelength degrees of freedom which is phi less than, but the cutoff has now been made into lambda by s. So this is a different theory with a different cutoff. So what do I have to do? I have to rescale and renormalize. So that is very easy process to do, and in this case the coefficient of gradient phi square is still 1. So the renormalization factor for the field will be exactly what we had at the tree level, and you can see now that if when I go through the process that we have gone through in the many times before, we will see that this Rs will take 1 Tu to 1 T plus n plus 2 all this stuff s square u times s to the 4 minus t. Okay. So now for the first time you see that the RG transformation is simply not taking t to t and u to u. It is mixing these things. So for example, t has now picked up a piece from the u and so on. And so you can already see that our naive intuition of simply doing dimensional analysis may not work here, because you see dimensionally the physical parameter associated with the interactions are different from, the dimensions are different from what multiplies phi square and what multiplies phi to the 4. But when you actually do this process of finding the effect of the short wavelength modes on the longer wavelength ones, you see that through the dimensionless coupling constant they will start talking to each other in a nice way. Okay, now this is the RS transformation, which is of course very nice, but we would like to get to the flow equations, and the flow equations can be understood by derived by just looking at the structure of this IDSTA that I mentioned in the couple of slides back, and just working out some math associated with that. And when we are going to do this flow equations, we don't want to work with arbitrary large s, we can work with small s but slightly greater than 1. And there this IDSTA can be easily shown to be approximately, I shouldn't say equal to, approximately equal to 1 by s when s is approximately equal to 1. Okay. So the order u renormalization group equations, I will just allow you to do the calculations yourself, it's actually very straightforward. You will see that dt by dl will be 2 times t plus 2 times t of l plus n plus 2 cd, cd is that ratio of sd by 2 pi to the d, ul, that ul is coming from this u, and this id remember has this 1 plus t, so that is this 1 plus t that is shown. Okay, so this id1 has this 1 plus t, and that is what is showing up. So that is the renormalization group equation that you have, and this du by dl is exactly the tree level because at this stage nothing has happened to you. And like I said, for the first time we see that in this RG equations something related to symmetry is showing up, right. So you see that this n plus 2 has shown up here. Okay. So what do these things teach us? So the first thing when we see RG equations, we will just like to pull off the fixed points. So if you pull off the fixed point, you will see that the equations have only one fixed point, which is the Gaussian fixed point. But what happens now is if I look at the eigensystem, of this linearized operator, so you see if I write this as linearized equations about t equal to 0 and u equal to 0, you will see that that's determined by this matrix. So effectively this is like that LS kind of matrix, but you should think of it as like DL by DLS by S DL by DS, something like that. So you will see that this is that matrix, and if you now try to find the eigensystem of that, you will see that there is one eigenvector which is the 1 0 vector, that is this one, and its eigenvalue will correspond to mu t equal to 2, right. So that is this 2. And if you look at the other eigenvector, the eigenvalue will be 4 minus t, but the eigenvector is not 0 1, but it is something else. Okay. So what we find is OT is a relevant direction, that is OT. OU is also a relevant direction, but OU is no longer just going up like this, it is sort of going up in that way, right. So this OU has both phi square p's as well as phi to the 4 p's. So I move, if I have a little bit of u in the problem, that is if I start off at my UV level, at my when I built my Ginzburg-Landau theory, I said that okay, I have to do some phenomenological guessing, and I figure out some value of u. So if that value of u is small and positive, and you are here, it will start to flow away in this direction. What does that mean? That means if you go along this direction, t is becoming negative. Why is t becoming negative? T is becoming negative because the idea is that if it is going to flow to some other fixed point, that fixed point somewhere here will have a positive value of u but a negative value of t. And why is it negative value of t? We believe that this will correspond to our ON critical point. The ON critical point at the Ginzburg-Landau saddle point level, the critical point would have occurred at t equal to 0. But now in this theory I have fluctuations. I am taking fluctuations before even I compute Tc. So the Tc that I am going to compute will be also including fluctuations. because the fluctuations are included, it's natural to sort of anticipate that the T will be smaller than the TC will be smaller than the TC associated with our original problem evaluated within the Ginzburg-Landau framework or the saddle point framework, and therefore you will see that this flow direction is what we will sort of guess from simple physics consideration of the fact that fluctuations will tend to destabilize an ordered phase, and therefore the TC when fluctuations are included will be lower than the TC when fluctuations are not included, right. So remember, the mean field kind of TC is what is the TC of the saddle point Ginzburg-Landau theory. So that has really not this kind of fluctuations included. Okay, so this is a remarkably helpful calculation. It hasn't given us a new fixed point. There's only one fixed point yet, right? But it is telling us that the relevant direction corresponding to the other operator is sort of going in that direction, which is already telling us what direction we should follow. We should follow the direction of trying to go along this, this path and try to see whether there is some fixed point there. Okay, so this is what we have to do. So we have done to order 1. So the natural next thing to do is to do order 2 in little u. Okay, so if you go and try to do calculations unaided in this area or in this field of study, you can end up doing a lot of calculations without and then run into difficulties and so on. So what I am going to do is, I am going to adopt a somewhat pragmatic strategy towards trying to compute this fixed point and also the critical properties. So I am going to use the knowledge of people who did this for the first time, and I am going to do only those calculations that are essential for us to get to some result at least up to some order of accuracy. So to do this, if I try to compute everything associated with this, it will take us a long time. So I am going to argue in this slide what are the things I should compute from this connected diagrams at the second order. Okay, so first observation is, you see that this action is whatever the effective action that we got from the first order. Now comes the point, minus the square of some quantity connected diagrams at the second order. So based on just this statement, it is quite natural to believe that the RG flow equations, if you compute to the next order in U, will change dt by dl to something at u square and du by dl minus au u square. So the claim is that they will simply change by negative quantities, where we just argue just by looking at this that at and au are positive numbers. Now this can of course be checked after we have done this calculation. Okay, so you will first realize that, so the more important check is to check that this au is positive. I will show you why in a minute. Suppose au is positive, then you suddenly see that when you solve this equation, it will find you a new fixed point. So you will find that this is a quadratic equation in u, and when I say equate it to u, I will get u equal to 0, and there will be another fixed point which is u star, and that u star will look like this au is a positive constant. So it is 1 by au 4 minus d. So what it is telling you is that if I define a quantity called as epsilon, which is 4 minus d, I am imagining that d is some arbitrary parameter. Now you might be surprised by this, but just hear me out. If I imagine that this is 4 minus d is a small parameter, then I can argue that to this order of the smallness in epsilon, which is 4 minus d, then this u star, the value of the critical coupling constant, dimensionless coupling constant, will be of order epsilon. Okay. So now if that is the case, then you see I will be able to find that the t star associated with that will be also of the order epsilon, and therefore you will see that this term will be of order epsilon square, whereas this equation is only up to order epsilon. This term will be order epsilon square. So what this is telling me is that if I want to do calculations up to order epsilons, then I don't need to worry about computing the corrections to t from second order terms in this action in U. I need to compute only second order terms in the corrections to the coupling constant, to the phi 4 coupling constant, but not to the phi square coupling constant. So there is a way to say this formally that we are going to do loop expansions, etc. I will not go into all that, but I just want to tell you that this idea was actually discovered by Wilson and Fisher, and they realized that if you treat 4 minus d as a small parameter, then you can organize this calculation as an expansion in epsilon, and what that will do for you is that all your critical exponents, and all the critical exponents are the eigenvalues of the logarithmic LS operator, the logarithmic derivative of the LS operator, remember, those can be the eigenvalues can be expanded in power series, some kind of asymptotic series actually, in epsilon. So this is what they realized. So I am going to use that knowledge in organizing my calculations. So when I do the calculations for this connected components, I will not calculate terms that contribute to t square, to the phi square, phi less than square, which will change the value of t. I will only calculate contributions that will change the value of the phi less than to the power 4 term, okay, in this fashion. So the strategy is the following: we will compute everything that contributes to phi less than to the power 4, but we will not compute terms here. It's not that they are 0, we don't need them if we want to compute answers to order epsilon, epsilon being 4 minus d. Okay, so this is the idea. Okay, so now let us, you see that we have a long road to calculations, so we have to organize our work carefully. So you see, when I take this, okay, so I start with this thing, okay, there is a small typo here, this is the square of this. If I take the square of this will involve two integrals, integral over dx1 and dx2, the phi terms which are functions of x1 and the phi terms which are functions of x2. So in total there are 25 terms here, 5 times 5. Now of the 5 times of the 25 terms, 5 of those terms are diagonal square terms. That means that this thing multiplying with x1 and the other thing with the same thing with x2. So those kind of term will appear only once. So there are 5 diagonal terms or whole square terms, and there are 20 cross terms. Cross terms meaning, for example, this term with say this term, one x1 and one x2. So you would have also got that similar thing coming from this x1 and this one x2, but x1 and x2 are completely arbitrary, so these are actually the same terms. So we need to compute 15 independent terms, and every time I have a non-diagonal or a cross term, I have to multiply it by 2. Okay, so 15 terms. So you may want to, pause the video and get a good beverage. Hopefully that will keep you awake, right? Okay, so let's continue. So I'll start with the first term. So the first term will come, this 4, I'll just explain one term at least in detail. So this 4 and this 4, that's 16, and this quantity evaluated at x1 and that quantity evaluated at x2. Remember the diagrams associated with this. We had seen a couple of slides back. I'll just remind you here. That is this diagram with itself. Okay, now I do the contractions. When I do the contractions, I have to contract 2 of the phi greater thans and another 2 of the phi greater than. So I'll get 2 Green's functions square. And there is a number 32 that I've written here. So this will come from 16, all the different contractions. There are various factors that you will get. You should figure it out yourself. You have to work through this, and you will see this result. Okay. Now please watch what I am doing here. There is an integral here which is dx1 and dx2, and from this line I am suddenly jumping to there is a single dx and there is a dr, and this has been made phi less than x to the 4. So it's as if x1 and x2 have been kept fixed at x or something, and I'll show you how that happens in the next slide, but just believe me that when you start with this and go down here, you will end up 32 times this is an integral over r of gr. So it's like x2 minus x, it's x, okay, so there's a typo here. This is x2 and this is x1. So this is x2 and x1, so that should be x1 here, right? And so you will end up getting this result here. Okay, so you will end up getting this. So how did I get this? So here is the important concept here. So this will be used throughout the calculations. So to do these manipulations, I have to understand how to do integrals of this kind. So it's f of x1, h of x1 minus x2, f of x2, dx1, dx2. Okay, just pardon my typo here. So this is g x1 x2. So remember, g x1 x2 depends only on x1 minus x2. So this whole thing has the form like this: f of x1, h of x1 minus x2, f of x2. Now you know that these Green's functions, so you are working at some finite t, etc. They have some cutoff, and so they have some short distance and all of that. So what I'm going to do is I'm going to change coordinates. So instead of x1 and x2, I'm going to go to the center of mass, which is x, and the relative coordinate, and now I can write this as f of x1. So first integral becomes dxr. This is f of x1 plus r by 2, f of x plus r by 2, f of x minus r by 2. So these are the f, and this becomes h of r. Now what I do is I do an expansion of this f about this x. So I can write this as a power c as some Taylor expansion. So it will be like x plus r dot gradient f and so on. So I'll end up getting this. And you see, this comes the minus, that comes the plus, etc. Now what I'm going to do is I'm going to now sort of keep the terms that don't depend on r with the f. So I'll get fx square and I'll get integral dr h of r. This is what happened in going from here to here. I kept only the term that is associated with the center of mass positions of x1 and x2, and for that I will get this phi less than x to the power 4. So you may wonder what happens to the other terms. So that's the beauty of this game. The other term is that you see they will show up with powers of gradients, but we know that if I have gradients on the fields, they will give me irrelevant operators. So what RG is doing for you is when you do this integrating out these modes, it will generate new operators, right? It will generate new coupling constants, but we only keep the relevant terms that are generated. Irrelevant terms we throw away because when we scale they will anyway die. So this is why I went through this calculation to show you the importance of this term here, because you see from this full calculation we only pick out the terms that give the relevant operators. We don't keep the information that gives us irrelevant operators. And you will be very careful in doing this calculation and checking whether the new terms that you are generating are relevant or irrelevant. If you start generating more and more relevant terms, then of course you are in trouble. So in this theory, of course, it doesn't happen, everything is nice. So this is how this whole calculation was done here, and we were able to start from here and reach this point. Okay, very good. Now I'll go a little fast with the discussion because I have explained the main key ideas. I will just stick to terms that are important. So if I now take the cross term between the first two, I will end up getting a term that contributes to phi less than square, and it looks like this. So you see there are two legs here associated with phi less than and two integrals over the phi greater than mode. So this will definitely contribute to phi less than square, but I am not showing the computation for that here because I am only interested in things to order epsilon square. Okay, let me move to the third term. This term has odd powers of phi greater than, so we don't need to calculate it, it's gone by symmetry. If I look at this term, okay, that same typo is here, it's x1, x2, okay, and you will get exactly the same answer one more time. It's precisely the same answer as before you will get from this term, which is the term number 4. If you look at the other terms, this cross fifth term, it is terms product of this vanishes because of odd powers of phi. If you look at this particular term, it is everything associated with phi greater than, so that just contributes to shift, so we don't even bother looking at it. If you look at this term, the 7th one, that vanishes by symmetry. If you look at the 8th term, which is this, you will see that that contributes to the change of t, or it generates a phi less than square term, so we don't worry about it. This vanishes due to, the 9th one vanishes due to symmetry. Okay, now comes the interesting one. I look at the 10th term, which is 3 powers of phi less than 1 power of phi greater than, and 3 powers of phi less than 1 power of phi greater than. Okay, what do we do here? Now, you notice that it will actually generate a new term. Okay. The most interesting thing is that that term is not relevant. So if it is not relevant, we don't worry about it. That's the point. Okay. All right. So this is, I hope you get the gist of the idea. So it will, so RG will generate all kinds of terms, as you, in fact, it will generate every symmetry allowed term it can generate, right? But we only keep relevant terms. Okay. And now this term vanishes due to symmetry, and this term also vanishes because of an interesting reason of this integral going to 0 and so on. Okay. And finally, we will end up getting this term which also contributes the same kind of diagram, but the way this term appears, it is phi less than square, phi greater than square, phi less than square, phi greater than square. It produces terms that depend on symmetry. This we had also seen in the first order result, and so you end up getting this 8n here. Again, the same type of x1, x2 is here, so please mind that. Okay. So you will get this answer, and you will see that now here there is this I2 sitting here because it is the integral square of this one, and that is coming from that. Okay. And finally, this term vanishes. Okay. And the last term comes from 3 phi greater thans, 1 phi less than, contracting with 1 phi less than and 3 phi greater than. So if you work out through the contractions of this, you will see, you will get a term like this, which is 0 at least on the phi less than square, right? But the second term here, if you work through this very carefully, and it is somewhat hard to do this within this Wilsonian momentum shell framework, you will see that it will actually change gradient phi less than square, but it will change to order epsilon square. Okay, it will not change to order epsilon because you see there are 2 u's here. So to order epsilon, I am not going to compute this. Okay, and practically because it is also somewhat difficult to do that computation. Okay, very good. So now we have come to the point where we have got an effective action for phi less than, and we have only kept, I will just repeat what we have kept. We have kept order, we are going to do calculations to order epsilon, the renormalization group calculations to order epsilon. So we have found all changes to phi to the 4, phi less than to the power 4 term coming from the high large wavelength modes, from the short wavelength modes, and we have not taken the u square term into account into phi less than square term. So this term has only order u corrections, whereas this term has order u square corrections, and that's the correct order corrections if you count it in the powers of epsilon. So since we did not compute the so-called sunrise diagram, so this diagram has a name, it is called a sunrise diagram. Since we did not compute that, you see that the coefficient of this is still 1, and because it is 1, the renormalization factor for the field is still what is given by dimensional analysis. If this had picked up some other power of s or something, then you will see that the field renormalization will not be what is given by dimensional analysis. So you will get an anomalous dimension as it is called. And if we go through this process where, since we did not do any field renormalization here, you will see that zeta of s is s to the power d minus 2 by 2, and you just go through this, you will end up getting that Rs becomes this. So now if you work out what are the renormalization group flow equations, you will see that they will look like this, right. So you are invited to do this yourself, it is very straightforward. Okay. So you will end up getting this very nice looking RG equations. Okay. So now is the first happy news here, is that you will see that when I try to solve for the fixed points of this, I have to equate this to 0 and find the values of t and u which solve these equations. You will see that t equal to u equal to 0 is still a fixed point. So you have the Gaussian fixed point. But what is most interesting is that if you treat epsilon as small, then you can actually solve this analytically, and you will see that this u star Wilson Fisher, so this is called the Wilson Fisher fixed point as because it was discovered by Wilson Fisher. You will see that there is this u star which is 1 by n plus 8 CD. CD is that ratio of SD by 2 pi to the d times epsilon. So if epsilon goes to 0, this is 0 and t star is also 0. So then there is only one fixed point, right. And this is the value of the little t. So you see, because fluctuations are there, my transition temperature is shifted from t equal to 0 to a negative value of t, and that is what is found here. Okay. So both are order epsilon, and this is exactly what we said, that we will get all our answers to order epsilon. Okay. Now we have found a new fixed point which we are very happy about. Now the question is, does it have the properties that we want? So we can just quickly do some plotting of these flows, and you will see that this is, I have done it for d equal to 3 and n equal to 3. So this is done numerically, and you see that of course epsilon is not considered small here, but we can see, it will actually illustrate the point we want to make. So you see that if I start at the Gaussian fixed point, everything is relevant. So if I am anywhere away from the Gaussian fixed point, I will flow away. But look at what happens at the Wilson Fisher fixed point. If I move along this direction, then I flow away, right. But if I am moving, if there is a line here in which I will flow into this point, I will come to the sink. So this is a sink direction and that is the source direction, if you wish. So I have one irrelevant direction here and one relevant direction here, but this is exactly the kind of fixed point I am hunting for. I need only one relevant direction, because if I do not have any external field in the Ising magnet or Heisenberg magnet, if I just change the temperature, if I come below Tc, I will produce this broken symmetry phase here. And this is exactly what I am able to achieve in this picture. I see that there is this relevant direction and this direction is irrelevant, right. And so I think for the first time we can celebrate a little bit, because we have actually found something that we can actually use and study. So this, we believe, is the ON symmetric critical point, like what we find in experiments. Okay, very good. So now we have found a new fixed point with one relevant direction. Let us go and analyze the critical properties. So how do I do that? The way we do that is, we go to the RG equations and we do perturbation around the fixed point. So what I do is, I take the RG equations which I had here, and I write t is equal to t plus delta t star plus delta t and u equal to u star plus delta u, and I will end up getting this differential equation, linear differential equation. And you see, there is something very interesting that happens here. You see, if I try to find the eigen system of this, so this is like S d by ds of Ls. Remember that Ls operator, that this matrix here is S d by ds of Ls. So the eigenvalues of this will immediately give me the exponents. So when I diagonalize this, or I find the eigen system of this, you will see that it has two eigenvectors. One is OT 10, right? I am calling it t, but it is whatever it is that. So it is OT 10 to order epsilon, right? And this mu t, the exponent associated with that to order epsilon, is 2 minus n plus 2 by n plus 8. N is the factor that determines the symmetry, right? N is a number, not a factor. that determines the symmetry. N is 1 is Ising, N is 2 is XY, N is 3 is Heisenberg, and so on. And you see, this is for small epsilon, this is relevant. That is the relevant, that's the temperature direction. And there is some kind of, this interaction thing has given us a new fixed point, and it has produced some critical interaction strength. And around that point, there is this direction, unnormalized. That's why I am writing it as this squiggle here. This is an unnormalized direction in the parameter space, in the space of theories. So this direction with mu u is minus epsilon. So now this is very important to understand that it is an irrelevant direction, and therefore at this Wilson fixed point I have only one relevant direction. And so this is the critical point that we have been hunting. So now it's also time for us to pause and understand what really has happened. So remember, if you simply did dimensional analysis, this mu t, which is the tree level renormalization group, this mu t would have been 2. Now what you see is that this mu t gets a correction, and you see it is different from the tree level dimension of 2, and it sort of goes away from this naive dimensional consideration that we did at the tree level. So where is this coming from? As you can see, this is coming from the effect of the short wavelength modes showing up on the longer wavelength, the infrared physics, being affected by the presence of an ultraviolet, namely all these fluctuating modes, and changing the nature of their coupling constants. And it mixes up things with different physical dimensions to produce some new effective dimensionless constants, which then give you the critical expanse, right? Now the most interesting thing here is that the deviation from what is given by dimensional analysis has no other information other than the symmetry and epsilon, which is spatial dimension. If remember, epsilon is 4 minus t. So the only thing that seems to change these exponents from the dimensional values or the tree level values are the symmetry parameters, or the number that determines symmetry, that is in our case this ON, and all other details are forgotten. Forgot means that all other details have gone into the irrelevant operators and so on. So the relevant operators, they will organize themselves in such a way as to get you this critical exponents. So friends, I mean, it's time for us to celebrate, because these are the puzzles we posed for us to answer, and this renormalization group framework explains all of the things that we set out to explain. It explains the nature of the fact that there is universal physics near critical points. It explains why there are different universality classes. As you can see, the exponents will be different for different symmetries, different for different spatial dimensions. So we'll get distinct universality classes. So things that have a certain symmetry undergoing a certain kind of critical transition, they will all in a particular spatial dimension, they will all have the same critical exponents, because in the infrared all other details are getting into the irrelevant operators and they just go away, and the only relevant operators, they play this conspiracy in the way that we have shown here, and you end up getting this fantastically beautiful result. Okay, so now that we have got mu t, we can use our the scaling laws, and from there we can extract all other results. So mu t, if I simply use the fact that this determines the free energy in d dimensions, I can find alpha is equal to this, which is a very nice result. I will find nu, this is the correlation length exponent. If you did dimensional analysis, it would have been half, but now it is this. And of course, you see I have put order epsilon square because we have computed this only to order epsilon. So there is a systematic way to go beyond this. So you can do one more round, you can do what are called 2 loop calculations, and you can improve this, you can get results to order epsilon square. Calculation has been done to many orders. I will have something to say briefly about that a little later. And if you now use the tree level dimension of the magnetic field, which is d by 2 plus 1, which we had discovered in the last lecture. If you cast this in the language of epsilon, you see that this is 3 minus epsilon by 2. If you use that, you can pull off all the other exponents beta, gamma, delta, and you will also see from scaling laws, you will find that eta is 0 at this level. 0 meaning that if I just stop at all, don't put all this, that means that the answer is order epsilon square. But that's exactly what we found when we were doing the renormalization calculations. So when this term that we did not use to get the anomalous dimension, because it did not change the term gradient phi square, we did not do that calculation. We did not get the correction to the coefficient of gradient phi less than square, and therefore we did not need to do any anomalous field renormalization. That means zeta was kept, zeta was found to be equal to s to the power minus d minus 2 by 2, which is given by dimensional analysis. If you did indeed take care of this, then the zeta would have changed, and that change would have been order epsilon square, and you would have seen that the answer goes as order epsilon square. So you will get something like, epsilon square divided by n plus 8 or something like that. I don't remember exactly what will come, but it will be epsilon square divided by something related to the symmetry n. So this is what you would have, you will find if you do the calculation to order epsilon square. So remarkably, these calculations have been done to many orders, and they have been checked with experiments and so on. So it's a remarkably successful program. Okay, so we have seen quite a lot today, and these are very important ideas in physics as well. So I would like to summarize, and I want to really give you a bigger picture of what is involved in this and what are the main ideas that are there. So the first thing is, of course, the Wilsonian renormalization group hinges on this critical idea that at a critical point there is an emergent symmetry, and this is scale invariance, and it's characterized by some scale factor Rs. And the question really that one asks here is, how do we implement this as a transformation and check whether you are in a scale invariant state? And Wilson's great contribution was to figure out not only the underlying concepts, but also give a calculational scheme to implement this transformation in a very general way, in the sense that this idea can be used for different kinds of field theories. It can also be used in numerical calculations and so on. And the essence of universality comes from the fact that if you look at critical points and look at the operator structure around critical points, there will be only few relevant operators there. All other information is lost, and these relevant operators, they determine all the physics, and this is what is behind the scaling laws and the scaling hypothesis. And anomalous dimensions arise because the effective coupling constants of the long wavelength modes that are generated at these critical points come from the fact that the effective interactions between them are also mediated in a sense by short wavelength fluctuations. So what renormalization group shows is a way to see what information from the short wavelength or the ultraviolet shows up in the infrared, right? And they show up in the infrared in this very interesting way of changing t to t plus u plus t plus u plus u square and so on, like that. And there is a way this happens in such a way that you get this universality, and the critical exponents are determined by symmetry and spatial dimension. Okay, so all the stuff that we saw as deviations from saddle point Ginzburg-Landau physics, they can be understood within this framework. So we explain why we get universal physics, why there are different universality classes, why they obey scaling law. So in a sense, this completely solves the problem we set out to address. Okay. So, I have to tell you that these have been tested experimentally and they have also been tested numerically. You can certainly look out into the world of internet to figure out some spectacular checks of these things. I have to make a comment here that if you want to go beyond order epsilon, going to order epsilon square and so on, then it turns out that this momentum shell way of keeping a cutoff and then integrating out modes, etc., becomes fairly difficult and technically challenging. So, people came up with very beautiful new methods to do this. So, one of them is called dimensional regularization. So, that theory formally does not introduce any cutoff, but it uses a very interesting way of keeping track of infinities that show up if you do not have a cutoff by changing the spatial dimension to be a continuous parameter and sort of treating the infinities as poles of certain functions, etc., and sort of cancelling the poles by what are called as counter terms and so on. Okay, so this is something that we will not discuss here, but it is something that has been taken quite afar in the field and maybe could even be useful in some of your research problems. Over and above all this, I would like to emphasize that this idea of renormalization group has now taken a very center stage place in physics. We now understand that this is a framework to understand physical theories. That is, if you want to describe physical theories, then this renormalization group idea is a way to formulate the kind of questions that you want to ask and also use it for doing calculations and make predictions. Okay. So, this is what we will do in this chapter and we will conclude the chapter here. But you may, if you are perceptive, then you will realize that everything we did was near 4 dimensions. But we know that there is interesting physics in, say, 2 dimensions. So, for example, we know that in 2 dimensions, you cannot break a continuous symmetry. This is called Mermin-Wagner theorem. So, you might wonder, how does Mermin-Wagner theorem fit into this? So, how can renormalization group show me the existence of Mermin-Wagner theorem and stuff like that? So, this we will address in the next chapter and we will introduce a class of models which are called nonlinear sigma models and we will learn how to do renormalization group for them. And we will discover some very interesting connections between all the things that we have done in d equal to 4 and similar stuff will happen near d equal to 2. There will be a small parameter around d equal to 2, etc. So, we will work on that and I am sure you will want to join me for that and I will see you in the next lecture. Thank you.